Okay, so this is lecture 25, and we have the remaining lectures, lecture 26, 27, and 28. So 28 will be the last lecture for our semester. And we will go through the circuit simulation today. So although our semester is devoted to the simulation of semiconductor devices, but that is closely related with the simulation of a semiconductor circuit or electronic circuit. So we will talk about it, and quickly we will come back to the device simulation. And one purpose of today's lecture is to introduce the capability to perform transient simulation. So transient simulation means that time varying simulation. Up to now, we have thought that every quantity, like for example, time derivative of electron density is identically 0. Also, time derivative of hole density is identically 0. Also, time derivative of displacement vector is also 0. So, what was our justification? What was our argument to say so? At the time, we restricted ourselves to the steady state simulation. So, by stating steady state simulation, then every quantity which depends on time is now becomes a constant over the time. So that was our magic keyword to greatly simplify our task. However, there are many physical things or simulation jobs which actually requires time transient behavior. So today we will talk about the capability to perform time transient simulation. Okay. Also, one thing is something like this. For example, let's say we have a resistor and we have a capacitor. Yes. And there we apply certain sinusoidal voltage source. For example, like the voltage across our voltage source is simply given by V naught times cosine omega t. So here omega is angular frequency and t is time, and V naught is a magnitude or amplitude of our voltage source. So this is in a unit of volt, and here we have R and C. So what will happen to this system? Of course, since we apply certain voltage source to our passive element like resistor and capacitor, we expect that there will be certain current. Okay, so that current will depend on time. So once R is given and C is given and even V naught is given, then everything looks quite clear and straightforward. But point is, if we change our angular frequency, so which is closely related with our frequency, omega is simply given by 2 pi times f. Then when we change our frequency, then our resistor and capacitor will give different impedances. So therefore the observed electric current, I can change it according to the change of our frequency f or angular frequency omega. Okay, do you understand the current situation? Now we have certain load, electrical load, and it can have different impedances when we have different frequency values. So that is our major concern today. So we will try to simulate arbitrary time varying signal. This is just a sinusoidal, but you can insert anything you want and get the response of your system current with respect to your input voltage. So up to now, with our current simulation capability, we cannot perform such kind of time varying phenomena. However, today we'll talk about how can we simulate this time varying behavior. So let's go. So let's say that here we have a simple circuit, voltage source and resistor. This is quite simple, but say that let's come back your current situation up to now. When I give you the homework, then usually I give you the structure drawn in this way, and please solve this system. That was your previous job. Given structure and solve the problem. But let's say that instead of this one, why don't you just solve this structure instead of this one? Let's just try to solve this structure, the structure whose channel region is tapered. Then what will happen? In this case, you have to develop your second code, which is designed for your second device. Of course, you feel that that is stupid job. You don't have to spend or waste your time about different devices. Think about today's job or your current work. So now you have certain structure and you build a code which takes into account this structure. So let's say that I changed my mind and give you different structure, blah blah blah, for example, something like that. If I give you this structure, then what will happen to your code? Actually, if you properly solve your homework, then your program should work even for this different structure, as long as I just to obey our rule. So our rule for vertex file and element file, and if you properly program it, then it should work. Just like this, let's consider our even simpler case of a circuit simulation. Here we have resistor and voltage source. Yes, it is really easy to solve this system. Then I can quickly make this system more complicated. Can make it more complicated by adding different elements, or another element, we can make it more complicated quite easily. So in this case, you build a certain code which is strictly valid for register and voltage source code. And when we include one more circuit element, if we have to rewrite our code again and again, then what will happen? You will be tired, and yes, you don't want to develop the code any further. That's the reason why we have to separate description about our circuit and solver. So user should not change the code. User should change only the input file for our system. Then solver takes over, and every detailed analysis done by solver. That is a right approach. So we have to follow that approach. So in the case of our semiconductor device, I just proposed one simple way, like specify vertex, and specify element. I think that is quite much reasonable way to describe our system. Just like this is for device, then we need one way to describe certain circuit. How can we describe our circuit? So please come back to our device. In the case of a device, everything is just given two-dimensional or three-dimensional structure. So everything is just homogeneous, and you can specify the position and their connectivity that were all to be specified. However, think about circuit now. In this case, the space is no longer a Cartesian coordinate, two-dimensional or three-dimensional coordinate. We need to deal with different circuit element types. For example, we have to be able to describe a circuit containing MOSFET, at the same time diode and resistor, inductor, capacitor, or voltage source, current source, or many other ones which are required to be in a single circuit. So this way, just specifying a position is not relevant. Also, actually, in the case of a circuit schematic, their connectivity is important. However, their position itself in the circuit schematic doesn't matter. I mean that in circuit, when I draw it in this way, or when I draw it in this way, is there any difference in the circuit description? So you can find that there is no difference between this schematic and this schematic. So they are identical. However, if I draw two different devices in my editor, then they are really different. So we have to understand, in the case of a circuit description, we have to specify the type of our element and their connectivity. So exact position is not important information. Then how can we specify a single element and how can we define their connectivity? So that is one point. We can, for example, think about this way. Think about one possible way. First, define one file which is describe the element. For example, let's say that we have a voltage source called VA and resistor called R1. Then in a file, I want to describe VA, also R1. Say that VA is a voltage source and it has electromotive force of 1.0 volt. So its magnitude is 1 volt. I want to specify that way. This one is a voltage source whose magnitude is 1.0 volt, and this is 1 kilo ohm resistor. I wanted to say so. That is one thing. This is description of each circuit element. And what is the next topic we have to do? Or the next task is their connectivity. For example, here we have positive terminal and negative terminal for our voltage source. And here we have also positive terminal and negative terminal for our resistor. Then what will happen? Then in this connectivity description, I wanted to say that positive of VA and positive of R1 are connected. Also, negative terminal of VA is connected to negative terminal of R1. I wanted to describe the system in this way. So, what is your opinion about my suggestion? So, in order to specify our system, I wanted to follow this two-step approach. So first, describe each circuit element, and second, describe the connectivity between them. So by specifying the terminals which are connected. So it sounds good. However, in reality, we do not follow this kind of two-file approach. Instead of that, we just try to merge them into only one single file. Then how can we merge those two files into one? So, for example, in the case of VA, I just say that VA is a voltage source, and description following this voltage source goes here. And also we can insert here certain connectivity information. So VA is a voltage source, and voltage source from its construction, it is assumed that it has two terminals. So the first letter and second letter comes in this position, and that position is corresponding to the connected node, circuit node for positive terminal and negative terminal. Then how about this? Let's just follow my own suggestion and the one which is more frequently used. So let me just write down. Of course, there is actually no such a thing, my own suggestion. However, just specify in follow my imaginary suggestion. So for example, VA and 1.0. Since this one starts from V, so by definition, it is regarded as voltage source. So by specifying just these two information, we will say that its name is VA and its motive force is 1.0 volt. And I wanted to say that R1. So also it starts from alphabet R. So it is a resistor, and 1000 simply means that although this is 1.0 and 1000, this is just unionless numbers. Since it is voltage source, it is interpreted as 1 volt. And since this one is resistor and this one is regarded as ohm. For example, if I say C1 10 to the minus 12, then what is the exact meaning of this description? So since this starts from C is reserved for a capacitor, so we will treat it as a farad. So it means that this C1 capacitor is a capacitor whose capacitance is 1 picofarad. So we can easily simplify our description for our system or circuit element by introducing reserved alphabet characters for them, and that is quite intuitive. So VA, this is the voltage source, and R1, this is a resistor. And then how about the connectivity? Then if so for example, I can write down this way, VA positive and R1 positive and VA negative, R1 negative. So simply this one means that, this one means that they are connected to each other. But don't be fooled by this stupid suggestion. This is not the way we follow. What is the critical point in this approach? What is it? What is missing? In my opinion, the critical weakness of this description is we have to see the entire circuit. I mean that since this is a so simple circuit, so just to specify their connection is not that difficult. But how about this? Now we have capacitor here. Then what will happen to this description? Then you can say now we have C1 plus and C1 minus, and say that this node has more branches. Yes, what will happen to this guy? Then whenever we add more and more circuit, then we have to add one more. These lines are not related with any specific circuit element. So we have to make a global look at the circuit schematic entirely and collect all the information out of it. So since this circuit is so simple, it is not that difficult, but for realistic one, that becomes an increasingly difficult job if we have more and more circuit elements. I think that that is the critical point we have to keep in mind. So what I want to say is, please localize. Description should be localized. So let's come back to your device description. At that time, what you did was just to specify positions and connectivity. In this case, you don't have to worry about anything about the entire structure of your system. Just to specify position and connect them. You just consider a single triangle. Then by collecting them all, you will get the entire circuit. However, if you do it in this way, then depending on the number of branches for a single node, the difficulty of your circuit description becomes increasingly high. So that is the reason why I think that this approach is quite bad. Then how can you localize this information or localize this description? Simply just to attach to our element description. Say that it has positive terminal and negative terminal, and also it has positive terminal and negative terminal. Instead of directly connecting this positive terminal and negative terminal, which can be several, if we have one more resistor, then we have to specify this one, they are connected. And if we have one more resistor, then we have to say that this one are connected. This is really tedious. Instead of that, just to concentrate on your current device, your current voltage source. Then say, instead of specifying all connected terminals, just to think about your connected circuit node. Oh, I think that that is the point. So the connectivity in principle should be regarded as terminal to terminal relation. Whether this terminal is connected to the other terminal, that is the original meaning of the connectivity. However, instead of that, we just introduce an intermediate instance called node, And now the relation, terminal to node relation, becomes now unique. So if we have more circuit elements, then terminal to terminal relations, there can be several of them related with this single terminal. However, if we just specify terminal to node relation, that relation becomes just one. For example, even in this 3-element case, we can say that VA plus is connected to out. R1 plus is connected to out, and R2 its plus terminal is connected to out. So you don't have to worry about entire connectivity. Just to specify what happens to my positive terminal and negative terminal. That's all. So I think that sounds quite obvious, but that is really big difference between our original suggestion, my original suggestion, and this terminal node-wise description about connectivity. So let's make a compact way. So I wanted to say this way. VA, now just specifying this way, we can easily understand this is a voltage source. And its name is VA. We can get these two information, and by specifying the voltage source, our next two words are resolved about the connectivity description. The first one should be out, because this one is reserved for our positive terminal, and 0, this 0 is for our grounded node. After this connectivity information is over, then now we can say 1.0. Since this is again voltage source, this simple scala 1.0 should be regarded as 1.0 volt. And go to next element, R1. So since this is R1, we have to reserve two spaces for connectivity, because resistor has two terminals, and specify out 0, out 0, and after that when you say that 1000, now this scala 1000 should be regarded as 1000 ohm. And you can see that by compactly expressed in these two lines, we can completely describe this circuit. But I think that compactness is quite an attractive thing in this description, but in my opinion, more important thing is, in this case, for connectivity description, now we introduce node information by specifying the node instead of connected terminals. That is the point. Okay, so node is the key component to describe the connectivity information. Then maybe you can ask me a certain question. Okay, professor, now we have this kind of description, but out or 0, how can you recognize that is a node? How can you understand they are nodes, and how can you distinguish them? Okay, so since they have different characters, out and 0, so we can say out and 0 are different nodes. And since their characters are the same, then this out and this out are identical. And also one more thing is, this not 0 is a special one which is reserved for grounded node. Okay, I think that I have covered very important topic in today's lecture. Then if we write a code for processing any kind of a circuit, then we should be able to read this kind of file format. So it is just a list of circuit elements. However, this description internally contains the connectivity information, and out of this list we should be able to build the connectivity information. So you know that this is additional effort from the developer side. Developer should extract certain connectivity information out of this file format and keep that information internally in their simulator. But from the benefit of user, this is significant. User don't worry about any connectivity problem. Just have a look at each element and specify the connected node from each terminal. So that is quite a natural way to describe our circuit. Now think about this simple RC filter. So we have voltage source, also R, C. They are serially connected. Then how can we describe this circuit without have a look at this one? So for why, just to neglect it. Then let me just write down in this way. V in. This one has two terminals, positive, negative, and positive is connected to in terminal, in node, and negative is connected to 0, and voltage is 1.5. I will write down in this way. And how about C1? C1, in this case it has also positive and negative, and positive is connected to in, and negative is connected to out, and it has 5 picofarad. So I will say just 5 pico. And resistor R1, it has again positive and negative terminal, and positive is connected to out, negative is connected to 0, and it has 2 mega ohm and say 2 million. Yes, that will be my way just to describe this simple circuit. So how about this? You feel that is really intuitive, and you can just mechanically follow this rule to make this so-called net list file format. And here let's come back. This is same with the correct answer. And one thing is, the appearance order doesn't matter. Whether V in comes first or V in comes last doesn't matter to this circuit description. So I think that if you have to develop circuit simulator, first of all, you have to pass this netlist file. So from this netlist file, you should extract the connectivity information. So of course, you have to also keep this information. Yes. So whenever you call C1, then you have to make a new object which is reserved for this C1. However, just describing R1 C1 bin, that is not sufficient for your circuit simulation. You have to also have information about in node, and you have to have information about out node. What is it? Which information is required for in node and out node? In node should understand actually V-in's positive terminal is connected to it, and also it should understand can say C1's positive terminal is connected to in. Also out node, in the case of out node, C1's negative terminal and R1's positive terminal. We have to have information about this connectivity. Also finally for node 0, we have to understand V-in's negative terminal is connected to the ground node, null node, and also R1's negative terminal is connected to the ground node. We have to keep this information. However, netlist does not give us that information explicitly. So we have to extract that information. Once we have information about node connectivity, let's say that anyhow you have that information, then circuit simulation becomes greatly simplified. So what is it? It is because why node-wise description internally is important, because you know the governing equation for circuit analysis is just Kirchhoff's current law. So that's the reason. So general rule is always consider a circuit and sum of current, outgoing current, should be 0. So this current component and this current component should have the same magnitude and different polarity or different sign. That is the meaning of Kirchhoff current law. So since we have to apply Kirchhoff's current law, so we need node information. So when you have a circuit netlist, please extract the node information, and for each node just to apply KCL. Then that's it. So I see that this the time is up, so it is much better for us just to stop here and continue our discussion in Wednesday's lecture. Although this is not directly related to the semiconductor device, but this is actually circuit simulation is actually the nearest neighbor of the device simulation, and they share many common features. So I think that this is important to be familiar with this circuit analysis, and you will find the common structure by comparing them, device simulation and circuit simulation, and your knowledge on device simulation can be even differ by this comparison. Okay, then see you Wednesday. Bye.